Thank you, Jared. And so I'm going to be talking today about subvarieties of tropical toric varieties. And I have to slightly apologize to people who are only here for the African math seminar, because I was asked, well, the organizers did tell me it was also an African math seminar. Somehow I took in more the Nairobi workshop. So this talk is partially more, well, I chose a topic that would be particularly, I think, good for people who, at the Nairobi workshop, I think you've been learning about toric varieties with the letter for the last several days. So I want to tell you a little bit about how toric varieties enter tropical geometry. And when I have to apologize, someone needs to let me know. I have construction next door, so let me know if you're not hearing me because of that. Okay, so that being said, let's get started. So the goal of the talk is I want to introduce tropical, so this is sort of the overall abstract something. I want to introduce tropical subschemes of tropical toric varieties. That's not meant to make any sense yet, but this is, I just want to tell you that this is part of a program that I've been part of for the past 5, almost 10 years, is now on the foundations of tropical geometry. Tropical geometry is a fairly new area at the interface between algebraic geometry and combinatorics, and it's sort of aiming to consider algebraic geometric questions from using combinatorial techniques. At the start, this was maybe more 19th century algebraic geometry almost, so the questions and the techniques would have been understandable to an algebraic geometry of the 19th century. Algebraic geometry has, we've developed a lot of new tools and techniques in the last, say, 150 years or so. And so this is part of a program to introduce more of this into tropical geometry. Okay, but let me come back to the basics of toric varieties. And maybe I should say, sorry, I'm just moving the chat window so I can see my slides, but I do encourage you, please do ask questions if you have them as you're going along, either verbally or in the chat. So what are toric varieties? For those of you who've been at the school for the last few days, you've been learning about them. For those who aren't, what I want you to know for the purposes of this talk is that they're combinatorially defined varieties. So varieties are the main object of study in algebraic geometry, and we're going to look at varieties that are defined by particular combinatorial data. They've had, maybe I would say there's sort of 3 different phases of studying toric varieties, and these of course are not precise, they overlap. I think in the first maybe 2 decades that people were studying toric varieties, they were used as a source of examples or counterexamples. So one of the advantages of toric varieties is that they're varieties defined by combinatorial data, and we have a complete dictionary from this algebraic geometry property turns into this combinatorial property. And so sometimes you have a question that you'd like to study in algebraic geometry. If you could turn it into a combinatorial question, it might be easier to study there. So I think that was maybe one of the main sources of maybe good success in the first few decades of toric geometry. So some examples are birational geometry of toric varieties is much easier than usual birational geometry and much better understood. And there's also just some elementary examples in algebraic geometry where it's easier to give a toric example than it is to give a non-toric example. One I personally like is for beginning algebraic geometry students is an example of a variety that is complete but not projective. This is somewhat complicated for the non-toric example, but fairly straightforward as a toric example. The next phase for toric geometry, I think, is to think about it as a good toric varieties as a good ambient variety. So this is generalizing embedding varieties into projective space. So when you first, if you describe algebraic geometry to a non-algebraic geometer, you might say we're looking at the solutions to polynomial equations in some ambient space. Classically, that was often projective space. I think it's been increasingly realized that sometimes if you choose a toric variety carefully, then this is going to give you, the toric variety will tell you more about the space. And I wrote, this is not precise, I wrote late 90s onwards. I was thinking there of things like Batarov's mirror symmetry, so studying hypersurfaces in toric varieties, being interested in mirror symmetry in physics. But it actually really goes back earlier. So some of Mumford et al.'s motivation originally to study these things were as part of toroidal compactifications for moduli of abelian varieties. So this has always been a theme, but I would say it's been a bigger theme in the last 20, 25 years. And then another theme more recently has been that toric varieties appear surprisingly often in applications. So if you have applications of algebraic geometry, often this will come in some other system. You have a system of polynomial equations, and sometimes they come as cut out by binomial ideals. So you've got this monomial equals this monomial. And this happens surprisingly often, particularly, for example, in statistical applications, but also many other places. And that's been something that's been a really big theme over the last 20 years. For this talk, I want to think about it maybe more as the good ambient variety, and maybe more it's as we generalize away from the idea of literal toric varieties to generalizations, how does the fact that a toric variety almost comes with natural coordinates, and how is that useful for us? So that's going to be maybe one of the big themes of the talk. This is the other theme. The other theme is to say toric varieties don't really care about where they're defined. So toric varieties are varieties that make sense first over any field. So those of you who've been at the school this week, hopefully you know that when I draw a picture like this, just the positive orthant, as a toric variety, I am drawing the affine plane. So this tells me the coordinate ring should be the polynomial ring in two variables with coefficients in my field K. And most of the properties of this don't really, I mean, we're not caring so much about the field K. So this is K squared, it could be C squared, R squared, depending on your field K. I mean, it's not quite 100% true, as the experts will know, that toric varieties don't care about the field. There are going to be some properties that do care about what field you're working over, but to a large degree, many of the properties, and particularly when we're talking about subvarieties, is we're not going to care structurally about what field we're working over. In fact, we could work over any ring. You might even go straight to working over the integers. So we can look at spec of z adjoin xy. So we'll just replace my field K by the integers, and we get a perfectly good operation. This is just the affine plane over the integers. And there's even a generalization of this where we can think about if you work over a valuation ring, you get this idea of families of toric varieties. So these are toric schemes. And there we have a combinatorial dictionary where instead of drawing pictures like this or polyhedral fans, we draw these polyhedral complexes. And it's down here. So these are somehow the idea is we're just looking at the combinatorics here. We're forming rings like this, and what the coefficients are they play some role, but they don't play an enormous role. That actually means that, well, not only do we not need division in a field, we can pass to a ring. Turns out we really don't need subtraction that much either. So we can pass to a semi-ring. So a semi-ring, as I'll say more about on the next slide, is where we have more or less a ring without subtraction. If you take that to the limit, you can even say, and I'll wave my hands at this in a few slides, we can even pass to the field with one element, so F1. F1, so as most of you presumably know, there is no such thing as the field with one element, but we can still build a geometry as if it did exist. One of the axioms of a field is that it should have two elements, 0 not equal to 1. But we still get a geometry that behaves as if there is a field with one element. And you can think of this to a certain extent as saying Well, one interpretation of part of F1 geometry is to say, let's think about toric varieties over no base field, no base ring, no base object, and to see the extent to which this makes sense. Okay, so that's the sort of, that's a little vague, but it's kind of a manifesto statement. We're going to look at toric geometry, but we're going to try and not pay attention to the field. Before I do that, though, let me say some more about semi-rings and introduce one of my favorite semi-rings. So a semi-ring is just a ring without subtraction. Okay, so technically that means addition is a monoid or a semi-group rather than a group. So my favorite example is probably the tropical semi-ring. So I will write R bar for this. There is no standard notation for this. I've been at tropical geometry conferences where I think literally the first 4 talks all used different notation and different conventions for what they meant by the tropical semi-ring. For me, it's going to mean R union infinity with 2 operations, tropical addition, which is minimum, the usual minimum of 2 numbers, and tropical multiplication, which is the usual addition. So we get things like 5 tropical plus 8. That's the minimum of 5 and 8, so it's 5. We get 6 tropical times 7. That's 6 plus 7 in normal arithmetic, so 13. And so then we get 6. Now I've managed to get all your photos, pictures over this. We get 6 times 7 plus 8. So just to check that I have everyone on the same page, maybe we can pause and if I can get some people to type in the chat. In tropical arithmetic, what would 6 times 7 plus 8 be? That's maybe a good point to pause for some questions, and if maybe some people could type in the chat at what you think the answer is to 6 times 7 plus 8. So I see, just give you a moment to think.
There is an answer in the chat.
All right, yes, okay. Sometimes I was hoping, sometimes when I do this, we get a whole bunch of answers, but good. Okay. So yeah, so I can see with 2 correct answers, we have 6 times 7 plus 8. 6 times 7 we've already decided is 13. 13 plus 8, minimum of 8 and 13 is 8. 8, so great. 8, okay, so people are on the same page. I see a question. Okay, a question. What about infinity? So is the question, how does infinity add? So infinity, go ahead. Yeah.
No, excuse me, please. The question is, what about minus infinity? Because I only see the symbol infinity.
Right, yes, no. So I'm only going to have plus infinity. I'm not going to have minus infinity. You might have seen, so sometimes you might have seen the tropical semi-ring with a minus infinity and with min replaced by max. So we can't, so I don't know how to add in minus infinity and plus infinity, because then you're going to have to answer the question, what is minus infinity plus infinity? Right, and then you're going to run into trouble getting a semi-ring structure. So we only choose, you have to make a choice. It is a choice. I've chosen plus infinity and min. You could equally choose minus infinity and max. Okay, and those would be both perfectly good answers. Well, they would be perfectly good semi-rings.
Please, in the case of minus infinity, the multiplication, will it also be represented by addition?
So that is one choice, yes. So you can look at what's sometimes called the max plus algebra. So this is actually old. So the name tropical semi-ring is a bit older than tropical geometry, so it's a bit before this century. Studying it under the name of the max plus algebra goes back to at least the 60s, particularly in optimization. And so one form is to have, well, one form is what I'm saying, min and plus. One is max and plus, though there with max you put minus infinity. There are also ones where we keep the multiplication as times. So you can think about this as sort of exponentiating this example. So there are many different isomorphic forms of the tropical semiring. It's one thing that makes this field, every talk has to basically start by explaining what they mean, which version of the tropical semiring they mean. Yeah, sorry, do we have more questions or? See a question about applications. Maybe I'll try and put that one off a little bit to the end, but ask again at the end if I haven't answered it. Let's spend a bit more time though just thinking about these two operations. The point you should take away from this is these two operations, min and plus, well, the technical way of saying this is that they form a semi-ring. They are like usual operations. You can check that they're associative. A plus B plus C is A plus B plus C. A times B times C is A times B times C. It doesn't matter where you put the parentheses, the brackets. If multiplication distributes over addition. So if I look at 5 times 8 plus 9, well, 8 plus 9 is 8. 5 times 8 is 13. But if I multiply this out, 5 times 8, that's 13. 5 times 9, that's 14. 13 plus 14 is 13. So multiplication distributes over addition. That was a proof by example, but you can check for yourself that minimum and addition distribute out. We can check that infinity is the additive identity. So the minimum of anything and infinity is your first number anything. 0 is the multiplicative identity. 0 tropical times anything is going to be that anything. So we have all the axioms of a ring, except that we don't have subtraction. Okay, so we're saying, so this is why it's called a semi-ring, and in particular, this one is the tropical semi-ring. Can we have a someone's asking, can we have a non-commutative tropical semi-ring? That's a good question. I don't know an example. So at least of a semi-ring of this form. I mean, there are non-commutative semi-rings, I guess, but ones that fit into this case, normally in tropical geometry, we focus a lot on these commutative semi-rings, and we even actually like semi-fields. So we like multiplication to have inverses. So division, we no subtraction, but yes to division often, because you can see, yeah, because multiplication is usual addition, we are allowed to divide in this case. Yeah, it's funny. I mean, there are a lot of generalizations of this, but I think this is part of it, is that just the tropical semi-ring by itself has been so useful that people haven't needed to explore so much. We haven't finished exploring all the applications and implications of just the tropical semi-ring so far. Let me give you one more example, and that's the Boolean SemiField. So this is, if you look at just, it's going to be the subalgebra of the tropical semi-ring R bar, just consisting of 0 and infinity. So the same operations, min and times. And I've just put above them in small letters is that I'm reminding you that infinity is the additive identity. It's playing the role of 0 in the usual arithmetic. And 1 is the multiplicative identity. It's playing the role of 0. Sorry, 0 rather is the multiplicative identity. It's playing the role of 1 in usual arithmetic. So I've written out here for you the addition and multiplication tables. So here you know that infinity is the additive identity. So you knew that this column would equal this column, and this row would equal this row. And then the minimum of 0 and 0 is 0. Here we have 0 as the multiplicative identity. So you knew that this column would equal this column, and this row would equal this row. And then infinity plus infinity we're setting to be infinity. And this is why we don't want to allow both infinity and minus infinity, right? Because then you'd have to worry about what does infinity plus minus infinity mean. Okay, So this is the Boolean SemiField. So this is, if I want to say I'm just going to forget about the coefficients, what I often mean in this setting is I'm going to work over the Boolean SemiField. That means I'm just going to remember, does a term show up or not show up? And that means algebraically we're in this world. And secretly, this is what people sometimes mean actually when they're talking about F1 geometry. So when they're working at the field of one element, the dirty secret is that the field of one element is not really a field. In some sense, you could think of it as a semi-ring with two elements. So it's a little strange, but we still get to say something about this. Okay. So those are my two favorite examples of semi-rings that we're going to be discussing. So maybe another good point to pause if there were any other questions about that. Okay, you can always interrupt later. Let's come to toric varieties and now to tropical toric varieties. So this is where, again, I apologize more to the African math seminar people that I'm going to assume a little bit that this will be a little fast for those of you who haven't just spent the last 2 days studying toric varieties. So what those of you who have seen toric varieties have learned is that the combinatorics we start with when we're talking about affine toric varieties is a rational polyhedral cone. So the rational means that I've got just integer points on each of these rays, and the pointed means that there is actually a vertex. Okay, so I start with my cone, like in this case, the cone generated by 1, 0 and minus 1, 2. And the first thing I do is I pass to the dual cone. So sigma dual is the set of all vectors whose dot product with everything in the cone is non-negative, or in a product. So here I've drawn the dual cone for this cone. You can see that every vector in the span of 0, 1 and 2, 1 that has positive non-negative inner product with every vector in this cone here. So 0, 1 has dot product 0 with 1, 0 and 2 with negative 1, 2. So it'll have non-negative dot product everywhere here. The same over for 2, 1 and so on. And then the next step is we have this dual cone. We look at just the lattice points in it. So just the points with integer coordinates. That forms a semigroup. We can add any two of those vectors together and we get another vector in the cone. And so we take the semigroup algebra. So that's, we write C adjoin sigma dual intersect M. So here M, it's a convention in toric geometry that we use the letter capital M for this lattice, but it's just going to be something isomorphic to Z to the N, in this case, Z squared. And I just take the semi-ring algebra. So in this case, I'm getting C adjoin Y, XY, X squared Y, and so on. Okay. You have to check, it's an exercise to check that I don't need any more generators. So Y corresponds to the lattice point 0, 1. XY corresponds to the lattice point 1, 1. X squared Y corresponds to the lattice point 2, 1. I'm just using the vectors to give me the exponent for X and the exponent for Y. Okay, and you have to check that every other lattice point in this cone, the corresponding monomial is is a product of these. So for example, 0, 2 turns into Y squared, which is just this generator Y squared. And you can check that this is actually isomorphic to, as a ring to, C adjoin Z1, Z2, Z3 mod the ideal generated by Z1, Z3 minus Z2 squared. And then the last step when we're defining affine toric varieties is to say, okay, that's great. I've got a good ring. I'm going to think about this as the coordinate ring of a variety. So technically we'll say we'll form spec of this ring. For any non-algebraic geometers in the audience, and so that means we have a ring, we have a set of functions, and we'd like them to be the functions on our space. And now what are the points of the space? The points of the space, or closed points being technical, correspond to maximal ideals of this ring. And that's going to correspond exactly to C algebra homomorphisms from the ring to the complex numbers. You should compare this to if I have a polynomial ring in 2 variables, then the homomorphisms from polynomial ring in 2 variables to the complex numbers, that's just going to be C squared. I just have to remember where does X go and where does Y go, okay? Again, to define a C algebra homomorphism from the polynomial ring in 2 variables to the complex numbers, I only have to tell you where is X sent, where is Y sent, and that determines the homomorphism. Okay, and that's going to be the key fact that we want to expand more on. And there. So the key fact again is that these C algebra homomorphisms in general only depend actually on semigroup homomorphisms from sigma dual intersect M to the complex numbers. And when I say semigroup, you have to ask what semigroup operations do we mean? We mean C with multiplication. Okay, so this is for the polynomial ring in 2 variables example, my sigma dual intersect M was just n squared. It was just the lattice points in the positive orthant. And I'm mapping them. I have things like 1, 0, that was X. I need, wherever it's sent to, 2, 0 has to be sent to the square of that number. So we just need semigroup homomorphisms from sigma dual intersect M to C times. And the point I want to make here is, and this is sort of maybe one of the key takeaway messages from this talk, is that sigma dual intersect M, that's purely a combinatorial object. It doesn't care about the choice of field. Of course, I've written everything here with the complex numbers, so it looks like it does depend on the choice of field, but this is somehow a less serious dependence on the choice of field. So this is the important bit is combinatorial. If you want to pass from C to R, it makes less of a difference. This is the same statement as when I said the affine plane. You can see that somehow there's a connection between C squared, R squared, your favorite field squared. They all are somehow the affine plane over their ground field in the same way. Okay, so that's the key point that we're going to focus on. And that's what's going to let us replace fields by rings and semi-rings, because we can look at homomorphisms. If we're only caring about semigroups, you can see that we didn't need C to be a field because we're only looking at the multiplication, and we didn't need it to be a group even. The multiplication, we only needed the semigroup homomorphisms. Okay. So that lets us make our general definition, which is if I start with a pointed rational polyhedral cone, like we do in always when we're talking about affine toric varieties, the tropical toric variety is going to be just, I replace where I had C on the previous slide, I've replaced it with the tropical semi-ring. And since I'm looking at homomorphisms of semigroups, I'm just going to want, before I said C with multiplication, so now I'll say R bar with tropical multiplication. And this is the same as if I had asked for homomorphisms of semi-rings from R bar join sigma dual intersect M into R bar. So we can think about this as the tropical coordinate ring of our tropical toric variety. But if I think about it just as a set, then I'm going to think about it as just these homomorphisms of semi-rings. So the first example would be, what if I look at the tropical affine plane? Then the homomorphisms of semi-rings, that's my sigma dual intersect M. Those were the lattice points in the positive orthant, so it's n squared. And I'm going to have homomorphisms of n squared into R bar. I just choose where 1, 0 goes. I choose where 0, 1 goes. I get R bar squared. And this is what you should compare to, you think about the affine plane over the complex numbers as c squared, over the real numbers as r squared. Here we're having over the tropical semi-ring, it's r bar squared. But I'll draw a picture of this this is my cartoon picture of the tropical affine plane. I've got my r squared here, and then these are my lines at infinity. So infinity, comma, anything, comma, infinity, and then just the point infinity, infinity. Okay, so we've tropicalized the affine plane, which just means think about the toric varieties, think about them with coefficients or as defined over the tropical semi-ring instead of over your favorite field. And these glue like usual toric varieties. So hopefully those of you who take in the school may have been learning that we could actually also glue together affine toric varieties to form more complicated varieties. The simplest example is the projective plane. The projective plane we can write as the union of 3 copies of c squared, just the 3 affine coordinate charts. So x0 not 0, x1 not 0, and x2 not 0. And we glue them together. I mean, this is the picture I drew for A2. I've chosen to draw the coordinates slightly differently for each copy so that we can see the gluing. And you can see that the boundary is gluing together. We have our 3 copies of infinity cross R, and we have 3 points that are of the form infinity, infinity, and they glue together to form a triangle that's compactifying our copy of R squared. So toric experts will notice that you're not surprised when I draw a triangle when I'm talking about the projective plane. Okay, so projective toric varieties come with families or collections of families, come with polytopes or collections of polytopes. And we're getting, in this way, we're getting exactly this, the tropicalization of that toric variety is homeomorphic to that polytope. The one thing that's a little different is normally actually to get a polytope out of a toric variety, you need to make an additional choice. It's a choice of an ample divisor. And here we're not making a choice. So it's homeomorphic, but it's not one particular choice of toric variety. Okay, so let's pause for a moment. That's tropical toric varieties. So what should you have got out of this if you're not really a toric person? And you should have got out of this that toric varieties are particularly nice combinatorial, a combinatorial class of varieties in algebraic geometry. And one thing we particularly like about them in this context is that they don't really care in a deep fashion about the ground where they're defined. So over what field or they're defined, they can make sense over rings, and they make sense over semi-rings. In particular, they make sense over the tropical semi-ring or the Boolean semi-ring with just these 2 elements. And this idea comes up, I mean, of just somehow pulling back to the basics of which lattice points, which monomials show up is something that's, I think, increasing across algebraic geometry. I mean, this is also a key idea, for example, in log geometry, which is having an increasing reach. Okay, but let me, in the rest of my time, tell you about subvarieties of tropical toric varieties. So maybe, I guess I should pause if anyone has a question before I get started on this part. This would be a good time to ask. Okay.
I have a short question.
Mm-hmm.
Could it be possible to say some properties of the tropical toric varieties when someone begins with an ideal, the defining ideal of the toric variety? For example, if one would write down the ideal, would one say some properties?
Yeah, I see. So so I could draw. Well, one thing I could do is I could draw a. I mean, if we're in a dimension where I can draw pictures, is if you give me the ideal of the. So you're thinking of maybe you have an affine toric variety that's cut out by binomial ideal, a binomial ideal perhaps. So there's a procedure called tropicalization that will just take that ideal and it will return for you a subspace in R to the n, but really it'll be a subspace in R bar to the n. And when maybe if I come back to my picture, to these pictures, as for example, if your toric variety was really a copy of P2, maybe it's embedded in P5, you would embed it in some big tropical projective space, but you would embed it in such a way that you would see this picture. So knowing that, I guess knowing the equations helps you to maybe see the to see the picture in the ambient, see the toric variety in its ambient space in this case.
Okay. Thank you very much.
Yeah, but it's all, I mean, as always with these things, it depends on what question you're trying to answer, whether a particular technique is useful or not.
Yeah, thank you very much.
So I have a question, please.
Mm-hmm.
Yes, so now in the cost ring construction, so you have this Toric variety and you want to tropicalize it. So, and it comes out that you have tropicalization of the affine space minus you tropicalize say variety of irrelevant IDs.
Mm-hmm. Yep.
Modulo tropicalization of the torus, right?
Mm-hmm.
Yeah, so how does that one fit into this? Because I didn't see that.
So that works in precisely the same way and in the way you would hope it works. So, I mean, let's think about let's just talk about P2. P2 is kind of the precursor of the Cox constructions. We're just saying P2 is C3, take away the origin, mod out by C star.
Okay.
So if you do the same thing, you would tropicalize your affine 3 space. So that's going to give you R bar cubed. We'll then remove the infinity, infinity, infinity. Maybe it's easier to talk about, maybe I'll talk about P1 instead of P2 actually, so I can wave my hands at this picture.
Okay.
If I take my A2, if I remove infinity, infinity, now the C star action or the the GM action that you normally quotient by to form P1, that tropicalizes to lines like this. So I quotient it by it, and what I get is the equivalent of a line passing across here. So you'd get a fixed point, an R, and then another fixed point. And the same way, for P2, I get the same thing. So maybe the punchline is the Cox construction works, tropicalizes absolutely straightforwardly. You tropicalize the affine space, you remove, instead of removing the irrelevant ideal is removing some strata. So some of these, some points like infinity, 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 and some infinity cross R and so on. And then the quotient will just be a quotient of topological spaces.
Oh, great. Thank you very much.
Yeah, so that works very nicely. Okay. Let me spend a bit of time now telling you about subvarieties of tropical toric varieties. And you see I've crossed it. Well, I made the title of my talk Subvarieties to not be scary to non-geometers. Turns out it's actually less scary to talk about subschemes. The reason for this is when we're talking about affine space, and I'm going to restrict myself to affine space or affine toric varieties for the rest of the talk. If I'm talking about a subscheme of a usual toric variety, that's just given by an ideal in this coordinate ring. If I want to talk about a variety instead of a subscheme, I have to start saying words like radical ideal. Maybe if it's irreducible, I have to talk about prime. These are concepts that we don't yet understand well from a tropical perspective. So from a tropical perspective, it's going to be much easier to just talk about subschemes, where we just talk about ideals without any extra adjectives. Okay, so an example, here's the simplest possible example. I've just got a line in the plane. So if my toric variety was affine space, then my coordinate ring is just C adjoint XY. I have the ideal generated by X plus Y minus 1. So I want the variety is just the line Y equals 1 minus X. So X plus Y minus 1 equals 0. if I want to look at points of this, you remember for the points of my toric variety, I said I can think about this as homomorphisms from the coordinate ring into the complex numbers. And I'm going to do that the same way for varieties. So I'm going to look at homomorphisms from the coordinate ring, so the quotient now by this ideal, into the complex numbers. So in the case of the line, I've got the coordinate ring mod x plus y minus 1 into C. Well, before, when I wasn't quotienting by x plus y minus 1, I just said I have to remember where x is sent and I have to remember where y is sent. But now I don't have complete freedom. I have to send x and y to numbers that add up to 1. And that's exactly the same as saying I'm looking at the variety, the set of solutions of the equation x plus y minus 1 in C squared. Okay, so that's the usual story. So that's subschemes, and this is the points, which is the same as the points of the underlying variety. Okay, so if I were to tropicalize this, a naive thing to expect would be that I could just consider ideals in this tropical semi-ring. So in the tropical coordinate ring, R bar adjoins sigma dual intersect M. So this was just the usual coordinate ring of my affine toric variety with my field replaced by R bar. Since I'm talking about semi-rings, I should tell you what an ideal is, but the shorthand answer is it's what you would guess it is. It's the same as for a ring. It's closed under addition, and it's closed under multiplication by elements of the ambient semi-ring, R bar adjoins sigma dual intersect M. Okay, so that's what we're going to do. We run into problems though. And the first problem we run into is, so maybe we should say, this is loosely what we want to think about. We do want to think about ideals in these semi-rings, but we're going to discover that we don't want to think about every ideal. And the first problem we run into is that this is not a Noetherian semi-ring. Let me give you an example in 2 variables. Okay, so this is the case again of the affine plane. If I have R bar adjoin x, y, then if I look at the ideal generated by x tropical plus y, that is properly contained in the ideal generated by x tropical plus y and x squared tropical plus y squared, which is properly contained in the ideal x plus y, e x squared plus y squared, x cubed plus y cubed, and so on, right? So at each stage, in the dth ideal, I'm going to add the generator x to the d plus y to the d. So in this way, we're going to get an infinite ascending chain of ideals. Just to be clear, why are these first 2 ideals not the same? If I look at, this is because we don't have subtraction in tropical geometry. So if I look at anything of degree 2 in this first ideal, it's going to come from something times x plus something times y times this, where all the operations are tropical operations. So we would have to have, if you multiply by x, you get x squared plus xy. If you multiply by y, you get xy plus y squared. So every term of degree 2 in this ideal has an xy term in it. And so there's no way we can get x squared plus y squared. And you can check that in the same way, your x cubed plus y cubed is not in this ideal, and so on. So we get these non-Noetherian ideals. So we get this infinite ascending chain of ideals, so a non-Noetherian ring. And not every ideal is finally generated. Yeah. Sorry, question? Yeah.
Can I ask this question?
Mm-hmm.
Yes. So, I'm a bit confused here when you say it's not Noetherian. By saying it's not Noetherian, it means that ascending chain of IDs does not terminate, right?
That's right. Yeah.
Good. Yes. But also, when we say it's not, being Noetherian also implies that every ID is finitely generated.
Mm-hmm. So I could take the ideal generated by all of these. So take the ideal generated by all of the x to the I plus y to the i's. I claim that that is not finitely generated.
Oh, I see. I see. Thank you.
Okay, great. Any other questions? Okay, great. Okay, so maybe so I'm saying that this is not Noetherian and this is a problem. So maybe I should sort of ask you, explain why do I think that this is a problem? To do that, I have to, so the answer to why I think it's a problem will only come on the next slide. I have to tell you how do I think about the varieties of these ideals? So in usual algebraic geometry, an ideal is defining a subscheme, but it has an underlying variety. This was this HOM from, if I go back 2 slides, I had my HOM from the coordinate ring into the complex numbers. So here we can do the same thing. There's one detail I'm going to not tell you about. It will have the HOM from my coordinate ring mod. Because it's a semi-ring, I don't quotient by the ideal. I quotient by what's called the bed congruence, which was something developed by Jeff and Noah Syracuse about 10 years ago. And I take this new semi-ring. This is the equivalent of the coordinate ring of my subscheme, and I map that into R bar. And this should be a subset of trop U sigma, okay? Because again, in trop U sigma was just the homomorphisms when I didn't quotient by anything. So I'm looking now at homomorphisms with a restricted condition. This can be interpreted though, rather than me telling you what this quotient, how to take an ideal and turn it into a congruence, I'll just say we can think about it concretely as the set of W in this homomorphism. So the set of maps from R bar adjoint sigma dual intersect M to R bar that have the property that whenever you have a polynomial in the ideal, the minimum of W of x to the U for the x to the U that show up is achieved at least twice. Okay, that's perhaps best seen in an example. If I was looking at x tropical plus y tropical plus 0, then we're looking at the minimum of when, so the W should be R bar squared because we only care about when x and y go. F tropicalizes to, we want the minimum of W1, W2, and 0, and we want the minimum of that to be achieved at least twice. So this is when W1 is 0, is less than or equal to W2 is 0 is less than or equal to W1, W1 is 0 less than or equal to W2, and W1 equals W2 less than or equal to 0. So this is our example. Right, I see a question about, is the tropical semi-ring is what we would call a tropical semi-field. So that's going to be Noetherian because there aren't that many, there aren't a lot of interesting ideals in the tropical semi-ring. There's only the infinity ideal and the whole ring. So from that perspective, that's fine. There's no infinite ascending chain of ideals because there's only 2 ideals in the first place. So that's Noetherian. It's just when we look at these coordinate rings of affine toric varieties or semi-rings of tropical polynomials, that's when it stops being Noetherian.
Please, one more thing, please.
I'm sorry. Sorry.
Can you hear me?
Yes. Yes.
Yes. So, according to what you just said, does that mean that the analogy of the Hilbert basis theorem does not apply here?
That's right. Right. So the Hilbert basis, exactly. So the Hilbert basis theorem is saying that it's exactly saying that the polynomial ring is Noetherian. Well, polynomial ring over a field is Noetherian, and we're saying this is not the case when you replace fields by semi-rings. That's correct. Yeah, so life just becomes a little harder when you work over semi-rings. Okay, good. Other questions? Okay, so I have to finish telling you why this is a problem. So if you haven't seen, if this is the first time you've seen with the word tropical in the title, this might have been a bit fast. The idea is this minimum achieved twice is one of the mantras of most presentations of tropical geometry. I'm choosing a slightly toric influenced one in honor of the workshop, but the idea is that from the ideal, we have a way of getting these pictures. because these semi-rings are not Noetherian, these ideals can be, these pictures here, the varieties can be fairly arbitrary. We can get things that are not polyhedral complexes. However, for ideals that come from polynomial or toric varieties over a field, there's a tropicalization procedure that basically says turn every addition and multiplication you see into a tropical addition and multiplication. When you do that, the varieties you get are polyhedral complexes with extra structure. This extra structure is what's called the balancing condition. And this is, if you've seen any talk on or any pictures on tropical geometry, you see pictures like this. It's a union of it's polyhedral complex, so a union of polyhedra glued together in a nice fashion. So the solution, and maybe I'll just say a few words about this, which this is particularly, I'm focusing on joint work of mine with Felipe Rincon, but then we've got an increasing sort of group of people thinking about related ideas in these foundations, is when we want to look at subschemes of tropical toric varieties, we didn't really like these arbitrary ideals, these arbitrary varieties, and we didn't really like this lack of Noetherianness. So we're going to restrict which ideals we consider. And it turns out there's a fairly simple condition. This is motivated by the theory of matroids that tells us, that lets us somehow artificially put back in enough subtraction into tropical geometry to get a more reasonable theory. And this goes as follows. I'm going to say that an ideal is a tropical ideal if I have the property that for every f and g in the ideal, where I have where f and g have the same coefficient for some monomial. So maybe x to the u is maybe x squared y cubed. So the coefficient of x squared y cubed is the same in both f and g. Now, if we were looking at polynomials over a field, and I had two polynomials where their coefficient of x squared y squared is the same in my ideal, then I know that I can take their difference and get a polynomial whose coefficient of x squared y cubed is 0. So the tropical way of saying that is I'm just going to impose it. I'm going to say that there is given f and g, whose coefficients are the same at x to the u, there is an h whose coefficient at x to the u is tropical 0, that's infinity, and the other coefficients are at least as large as of h are at least as large as the minimum of the two. This is a condition that comes from the theory of valuations, which I haven't told you about today. And the idea here is that h is a replacement for f minus g. It's replacing just enough of putting in just enough subtraction into the theory. So a non-example would be if I took the ideal just generated by x plus y. So and I took f to be x squared plus xy and g to be xy plus y squared. So then the problem is we have two polynomials in this ideal. Their coefficients for x times y are the same, but there's no polynomial in the ideal that gets rid of the xy term and has the coefficients, but has, the coefficients of x squared and y squared are at least as large, well, are the minimum because they're different. So that would mean it would have to be the polynomial x squared plus y squared in the ideal. So I guess I shouldn't, it's actually a typo to have the non-exist. It should just say h equals x squared plus y squared is not in the ideal. So this is the failure of, if I wanted a tropical ideal, I would have to put in this x squared plus y squared, and then actually I'd have to put an x cubed plus y cubed as well, and we get this whole infinitely generated ideal. The motivating example is to do this tropicalization procedure, which is I start with an ideal defining a subscheme of my affine toric variety over a field, and then I just tropicalize it by, for every polynomial in the ideal, I just remember the monomials. I take the tropical sum of the monomials with no coefficients, and that gives me an ideal which is a tropical ideal. And it will always satisfy the subtraction condition because the original ideal did. Why do we care about these? Well, the good news is if we have a variety of a tropical ideal, if I add the subtraction condition in, then the varieties are polyhedral complexes, and they satisfy this extra combinatorial condition called the balancing condition. So this means that they're the basic object that we study in tropical geometry. Another piece of good news is that tropical ideals obey the ascending chain condition. I showed you an example of an infinite ascending chain of ideals in the semi-ring of tropical polynomials. But in this way, you can't find an infinite chain of tropical ideals in the same way. So tropical ideals obey the ascending chain condition. And maybe the last thing I'll tell you about here is that they also obey the weak Nullstellensatz. So in the Nullstellensatz, there's this basic part of often a first course in algebraic geometry that tells you if the variety of an ideal is empty, the ideal has to be the whole ring. And in usual affine algebraic geometry would be the whole polynomial ring. For our tropical version, in the ideal generated by 0 is the whole semi-ring. So we're saying if the variety is empty, the ideal was actually the whole coordinate ring of my toric variety. And this is not true without this elimination condition, this condition on F and G that I just told you about. An example would be if I take the ideal generated by x plus 1 and x plus 0 in R bar adjoin x. The variety is empty because if you want the minimum to be achieved at least twice here, x would have to be 1, but it would have to be 0. So the variety is empty, but the ideal is not the whole semi-ring of tropical polynomials because there's no way to get rid of the x's. Okay. So the punchline, take-home message from this part of the talk is if we want to look at subvarieties of tropical toric varieties, we can start the same way as we usually do. We look at ideals in the coordinate ring, but we have to put on this extra condition, which is secretly a matroid condition. And from that, we get things that behave much more nicer in a more geometric fashion. And this is things. I mean, we know a few more things about this, but there are many more details to be worked out. And in particular, one of the things that still needs to be worked out is exactly what does irreducibility mean in this case, which is why I said I was going to tell you about subschemes instead of subvarieties. So maybe I should stop there.